Good day. My name is Patrick Conway. I'm a grad student at CU Boulder in the Master of Data Science program. In this semester, I completed a study based off of a news article that intrigued me. And you can see some of those images up here on the screen. A CNN report found that Navy Federal Credit Union denied half of their black mortgage applicants in 2022. They used the Home Mortgage Disclosure Act database and identified that this was an issue across industry for multiple lenders. And NFCU, or Navy Federal, had the greatest disparity for black applicants compared to other racial and ethnic groups and compared to other financial institutions. This initial analysis by CNN, for me, warranted further inspection and investigation. And this is what motivated my study. I wanted to further inspect and ask some key questions from a machine learning perspective. Is it effective to include protected class variables such as age, gender, and race as predictors in machine learning models? When including or excluding those values and variables, is the difference in performance significant? If so, by how much? And based upon the outcomes of any models built, how likely do we think it is that companies are including these predictors in any modeling that they may be doing? Why does this matter? It matters for several reasons, namely accountability. We as citizens want financial institutions to not engage in discriminatory business practices. We also want assurance that financial institutions are only making lending decisions based upon financially relevant factors. And we should have that assurance as citizens. And lastly, it's the pursuit of the American dream. Just about everybody in the United States dreams of having a place to call their own. Countless Americans cannot achieve this without attaining a mortgage to purchase a home. Having that accountability and assurance helps enable this dream. Knowing whether or not protected class information is impactful or effectual as a predictor in a machine learning model can help us get some of that accountability and insurance. So I'm going to talk a little bit about where I got my data and what I did for this study. I used the same source that CNN did, the Home Mortgage Disclosure Act, and pulled all of the information for the same institutions that they did for Navy Federal, JP Morgan, Rocket Mortgage, Wells Fargo, and Bank of America. I used their data dictionary to better understand the data formats before proceeding to cleaning. And I went from hundreds of thousands of records with blanks with missing values, etc., to about 200,000 clean records. Starting off, here's one example from Navy Federal with a bunch of sparse columns, some missing values, what have you, and hundreds of columns, some of them not necessarily relevant to the purposes of this study. So using that information, I was able to truncate things down and get to this data set that you see in front of you here. No blanks, inferred missing values, so that we can build effective machine learning models. After I went through that process, I jumped over to exploring that data. And I found some interesting things here when I was initially looking. I definitely found that the trend continued from 2022 into 2023 for that data in terms of black applicants. As we can see, the top line here across industry, fairly low. Navy Federal having below 50% approval rating in 2023, and kind of a disparity as well as we can see for some of the other lenders as well. What I also found interesting here was in the case of no race being reported. For Bank of America and JP Morgan, it was actually a higher approval rating than any other group on a racial basis. It was higher for Navy Federal compared to black applicants, and it was fairly high or kind of in the middle of the pack for the other two lenders. And I looked at that and wanted to say, okay, well, what does it look like for gender or sex and race? So we can look at that as well briefly here. In the case where that information wasn't provided on an application, it was near 100% approval rating for sex across all of those lenders. And the same was the case when we're looking at age. When that was not reported, near 100% approval ratings. So that gives me a little bit of hope that maybe we're not engaging, at least in the financial industry, in discriminatory practices on the basis of sex and age, at least in the case when that information is not reported, right? But it's interesting, right? We should look at this further through the modeling. We should look at it and see what the outcomes are when we try to train different machine learning models with and without this protected class information to see how effective it is. So from here, I want to transition over from some of this exploratory analysis to actually some of the models that were built. And the first of those that I want to discuss is the decision tree. So I trained two different models here. One was trained with protected class information, one without, and that's going to be the case across the board for the models that we show today. And the size is a little bit small. I'll apologize that, but I'll save your squinting. These trees are identical. They have the exact same features in consideration in each branch. And not only that, but the features are relevant to financial information. We're talking about debt to income ratio. We're talking about income of the applicant, interest rate, potential interest rate for the mortgage if it got approved, whether or not it's for an open-end line of credit, and what automated underwriting system was used to make the determination. And that's the case in both trees. And they both had pretty decent performance across all of the different metrics that we took in consideration for this study. Ultimately, what this means is that in the case of decision trees, protected class information did not provide sufficient information game over other available features to be high enough in this decision tree to make a decision or a branching feature. So with that, I think that about covers it for decision trees. I want to transition over to Bernoulli naive Bayes, which was actually a pretty great performer. What I did for this one is I actually ran both models, the with and without protected class information, 500 times. And I captured the performance metrics on each run of those different models to see what the distribution was. So that I could do a statistical significance test of the difference in means between those two distributions. And we can see here across the board for all these different metrics that the orange curve kind of comes out ahead of the blue curve. And it turns out that that orange curve is the without protected class model. It actually performs better than the with protected class information. And looking through here, it's a statistically significant difference as well. So, and in terms of those performance metrics, they're really high. We're looking at 94 to 96% with a ROC AUC score of about 90%. That's a pretty substantial and good performance for a model. Now, we can take this and compare it to logistic regression really quick. When we look at logistic regression, we see the opposite is true. We see that the blue curve comes out ahead of the orange curve and that it's a statistically significant difference with higher mean scores across the board for all metrics. And in this case, that's including protected class information. So that's a bit of a concern, right? But we can mitigate that when we actually look at the difference in means. So we can see here that for accuracy, that difference is less than 0.25%. And in terms of ROC AUC, that's probably the highest. It's a little over 0.5%. It is a statistically significant gain, but not a substantial numeric gain. So that's worth noting when we transition over to the conclusion section, and we'll get to that here after not too much longer. So from here, I want to jump over to one more model, and that is a support vector machine. For support vector machines, they are actually very computationally intensive, right? And I was not able to perform that same difference testing as I did for logistic regression or for Bernoulli naive Bayes. But I did a single run of the support vector machine, and that single run, its metrics actually for accuracy, precision recall, and F1 and ROC AUC were higher than the mean performance for logistic regression. And we cannot say whether or not the SVM is better with or without protected classes in this case because we didn't do that large cross-validation between the different models and do that significance testing. But even so, on this single run, at least in this case, the difference is still a fraction of a percent across all of these metrics, except for ROC AUC. In terms of ROC AUC, without protected classes is actually favored. So I found this portion really interesting as well. And then just visually, it's actually pretty stunning. If you look at these two graphs here of the predicted versus true, if we're looking at the without protected class information, the blue dots match up, the orange dots match up. You can see the accuracy in action. right? So we visited a few of the models that were built in this study, and I want to talk about what can we draw as conclusions from this study, and what can we infer. So here's a summary table up on screen in front of us of performance metrics for accuracy where we were able to do that significance testing. And out of three cases, which actually had a significant difference, two of them favored protected classes. One of them favored with protected classes, and it overall was the best performer in terms of accuracy where this test was able to be done. I do believe that if I had the computational power and the time available, that doing this testing on a support vector machine would likely outperform logistic regression. But due to resource and time constraints, I was not able to do that testing. And at least in the case of this top performer, it's a 0.25% difference, right? And if we're talking about a 0.25% difference, why incorporate that? Why build that when it's literally engaging in discriminatory practices and could bring a business to the point where they may have lawsuits, they may get hit with regulatory fines and fees, where you could have all sorts of problems. You could lose customers, right? And all of these models were built with publicly available data. And there's information that I did not have available to me that, if included in these models, would probably provide a larger performance boost than this small 0.25%, right? We're talking about credit scores, we're talking about applicant cash on hand to cover closing costs, and other financially relevant information. That would more than likely provide more than that 0.25% performance boost versus including protected class information. Not only that, but this 0.25% difference in the best performing model, if organization did choose to use something of that nature, it's likely insufficient to explain the disparities in outcomes for mortgage approval rates based on age, gender, and race. There's likely some other features, hidden features, latent features that are unavailable. So the perceived performance gain is really far outweighed by the risk. And I don't see it being likely that a company would include these in any of their machine learning models if they're using that to make a decision. And those are my findings. Those are my conclusions. This is my study. I hope you enjoyed watching with me today, and feel free to check out my website. It's pconnell.github.io/ml. Have a look and feel free to reach out. Thank you so much.